Well, hello friends. So today I have reached an interesting milestone with the emulator because it is now able to run itself. So if we run userspace emulator on the userspace emulator, we can see that it prints out its usage, and then if we throw him some command like echo hello, then it actually runs it. So what we have here is the emulator emulating the emulator emulating bin echo, which is pretty cool. But we can see that even something simple as just bin echo has a fair amount of slowdown, and when we ran bin ID, let's time it, we had a fair amount of slowdown as well. So slowdown is not so bad with one instance, but if you layer a second instance, so we emulate the emulator emulating bin ID, then we start to slow down quite a bit, and we can see the CPU usage up here take off into the 100%. And I actually posted a screenshot of this earlier today because I was happy that I was able to emulate the emulator all within a week. And it ended up taking like 43 seconds here, as you can see. So I guess I'm expecting something similar. But the mission today is to make this go faster, because I think the emulator being able to run itself is basically tells us that now it's really quite capable, and we can afford to spend some time on making it go faster. And it's still going. So let's see what kind of number we end up with here. 59 seconds, holy moly. All right, so probably it's slowed down quite significantly by me running the recording software at the same time. But anyway, today I think we should try to get this number down, preferably down to like half, at least half of where we are now. So like down to from 1 minute to half a minute. You know, something like 15-20 seconds would be really nice. I don't know really. We'll just use the profiler and go one step at a time. So systematic approach. So what we'll do is we'll just start running this, and while it's running, we will just grab a profile of PID 30. Oops. Enable that. And boom. Oh, should make that go away. Okay, so here we go, and we can see that we are spending most of the time in MMU find region. So, and most of that is instruction fetch. Right. Okay, so that's pretty much expected. The way that we fetch instructions in where are you? Here. The way that we fetch instructions is that we call read memory 8 if we want to read the 8 bits. We have a 16-bit variant and 30-bit variant. And doing a read memory means that we have to go to the MMU, and the MMU will have to look in the region table, because we have our memory regions in a table so that we can have memory from many different sources. Like you can have memory that you get from mmap, you can have memory that you get from the executable, we have the stack, which is a separate memory region, and so on. And whenever you do a memory access, we have to go and look in this region table, like where, which region is responsible for the address that you're accessing. But that's obviously pretty expensive. So it's the top of our profile here, find region. So since instruction fetch is the heaviest, I think one optimization that we can do here that will immediately pay off would be to not use to not use the regular memory reading API when we're fetching instruction bytes, but instead like cache a pointer to the next instruction. So we would have something like cached code pointer. We would have that, and then we would just increment it, just like we increment the EIP register. And then here we can say, like, if we don't have a cached code pointer, or if the cached code pointer has gone off the end of what we cache, so like cached code footer, cache code end, then we'll just update code cache. So this is not going to play very nicely with self-modifying code, but that's not something that we care about right now anyway. So let's see. And then here, this would be a +1 since we're doing a 16-bit axis. And down here, we need +3. Yes. That seems good. Or we can also write it this way. Maybe that's a little bit nicer. Okay, and then the same pattern repeats. So, okay, so where do we get these cached code pointers from? Well, basically, we get them from saying cached code footer is going to be that we ask the MMU for we look up the region that the code is coming from, first of all. So first we ask for the region that we're in, and then we say that, oh wait, hold on. This is a region. Okay, and then we assert that we find a region, because I don't want to deal with the case where we don't right now. And then we just ask the region for a cacheable pointer. To the current EIP minus the region base. So, and then we also need to ask for the end of the cacheable region. So that would be a cacheable pointer to region size. That would be one past the end of the region. Okay, and then we just need this API on our MMU region thing. So let's just add these members here to soft CPU before we forget. So that's like a U8 cached code footer. These can be const, actually, because we're only going to fetch from them. We're never going to write through these pointers. Okay, and then in soft MMU region, we'll just add it can be like an optional API actually, so like maybe not every kind of region would provide a cacheable pointer, so, or I don't know, but let's not worry too much about that. We'll just say like cacheable pointer to an offset, and if you don't implement this, we'll return null, and then this will crash, but that's okay, because then we can quickly figure out why. But in our simple region class, we will just implement this. So simple region, forgot to declare. And the cacheable pointer is, let's see, that's my data plus offset, actually. I guess that's the whole thing. Yes. but then of course we wanted to fetch 16 here, so this would be reinterpret cast to use 16. More taking advantage here of the fact that we're running on a little endian system. Like, we know that we're running on Intel, so we don't have to care about byte order. Makes this very easy. Okay. So now, let's see. So now when we want to fetch instructions, it will discover we don't have a cache code pointer, and then we'll update the code cache, which we didn't declare. But what that does is that it goes and finds the region for the current instruction pointer and then caches raw pointers into that region at the current DIP. So I think that'll probably work. I just wonder how much faster it is. Oh wait, cacheable pointer. Forgot something. Yeah, okay, fine. Maybe unused. Maybe. So let's see. So this should get rid of a huge number of those find region calls. Although, actually, this is not good enough because we're tying it to the EIP. So it gets tied to the instruction pointer. Like, whenever we do an update code cache, the code pointer now points to the current instruction. But what if you jump, right, or call, or ret, or something? Then we mutate the EIP. So when we set the EIP, we need to invalidate the code cache. So we'll just do this, which will cause it to get updated on next instruction fetch. Yeah, I think that's good enough. So basically what will happen now is that as long as you're executing instructions sequentially, then we'll fetch them through this pointer, which will completely bypass the region lookup. So let's see, UE bin ID still works, very good. And what if we run this thing? I wonder how long this will take. So let's see. I think this design is pretty straightforward and not much to think about really. So I think we're going to want it. So I'm just going to start writing out a commit. I just don't know how much faster it is yet. We'll find out. I forgot to say time here, but we also print out like how long something takes. Okay, so 29.9 seconds. We're already half. We're already 50%, or a 2x improvement, I guess you could say. So that's really good. Add a very simple instruction fetch cache to avoid MMU region lookup on every single instruction fetch. Now cache a raw pointer to the current instruction. This gets automatically invalidated when we jump somewhere, but as long as we're executing sequentially, instruction fetches will hit the cache and bypass all the region lookup stuff. This is a 2x speed up on, let's just say this is about a 2x. Yeah, so that's pretty cool. Okay, so then let's get a new profile. So let me use the GUI for this. Forgot that I added a GUI for the profiler selecting the process. Obviously, we should be using that. Okay, so now find region has been dethroned. He's now at number 4 here, so it's still pretty aggressively active code, except it's not at the top anymore, so that's a good thing. So at the top now, we have the instruction constructor. So basically what that does is that it takes, it looks at the instruction byte stream and just figures out what x86 instruction is this. And x86 instructions are pretty complex. They have a lot of things going on, like they have prefix bytes, and they have you know, like various addressing modes, RM bytes, SIB bytes, and multi-byte opcodes and all kinds of shit. And that is apparently where we're spending most of our time. And if we just scroll through the assembly here, nothing in particular stands out. So let's see. I'm thinking that we can probably inline it, and that will probably help us quite a bit. But we're going to investigate that in a moment. Let's just see what else is going on here. So read 8, this is the reading from the instruction stream. The code that we just edited. So let's see, so it's checking the cached code pointer here. We can see that just null checking that pointer is where we spend a whole lot of time. I don't know if that's really avoidable. Because the majority of the time it's not going to be null. So I don't know if this will actually change anything, but we could say that it's unlikely that it will be invalid. Or actually, it's not completely unlikely, because it will change whenever we flush the cache, because we're doing a jump. Okay, so forget about that. We'll leave that one as is. But there's a fair amount of just like entry and exit overhead here. So I think this is this could probably benefit from inlining as well. And what else do we have? We have find region, of course. We have a mov instruction. I'm looking very heavy. What are you even doing in that instruction? It's so much going on here. What is going on in that instruction? Let's see. Mov reg32 rm32. Okay, so looking pretty normal. So I guess that just expands to a lot of code. But all right, so here is some nonsense. Like this thing here should clearly be inlined. Update code cache. Well, it's going to take some time to do that when we hit that, obviously. Okay, so before we go any further, actually, let's make sure that we are compiling the stuff with optimizations turned on. So one thing that we do for the painter code, which it greatly benefits from, is that we turn on O3 compilation specifically for that file. So I think we're going to do that here as well. So we'll turn on O3 for the CPU file, and I think for the instruction file, and maybe for the emulator file. If we just, it's a little bit brute force-ish here, but before we go further looking for like optimization stuff, it's good to turn on like everything that the compiler can do by itself. So let's see, we have some. Okay, so whatever, if symbol is not null. I guess GCC thinks that this could be null suddenly when we're compiling with optimizations. I don't know why. I'm not going to investigate that now. Okay, so let's see, I should make an alias for this, by the way. So I'm curious how much this would do just turning on O3 for these files, because O3 means that we'll do like a lot more inlining automatically, and it'll be interesting to see what remains on the table after that. So wait, what happened there? Okay, it finished. So okay, so about 2.5 seconds off. So it's not fantastic, but it's also not nothing, so I'll take it. How much is that? It's 30,000 minus 27,575. It's like 8%. That's not bad. Alright, so let's see, userspace emulator plus libx86, turn on O3, optimization for emulation code. Since this code is performance sensitive, let's have the compiler do whatever it can to help us with the most important files. This yields a 8% speed up. Yeah. I mean, it's not perfect. The number is obviously not perfect, and it's just like a single test and a single run of the test, but it's more to have like some scale of the improvement we're talking about here. Because I feel like when people talk about performance improvements, they just say like, oh, it's faster, but like how much faster, right? So if you can measure like, oh, it's 8% faster, then it's a lot more interesting. Anyway, so now we'll need to get a new profile of this thing, obviously. Oh, and let me make an alias for that because it's annoying to type it out. Root home anon shell rc alias. Let's call it X for bin userspace emulator. Bin userspace emulator. Bin ID. Okay, so now we type X and we'll run the emulator in the emulator on ID. Oh. Should probably fix up the profiler GUI here to look a little bit nicer, but it works. Okay, so now after we have turned on optimizations, this here immediately looks stupid to me. I know that this needs to be inline, but it's not. And this is another thing that should be inline. So there are probably a number of things here that should just be inlined, basically. Like this could be inlined. These could be inlined. This could be inline. Yeah, okay, so there's a fair number of things to inline here. Let's see. In the instruction class, let's make sure that we, you know what, let's just go all in here. Let's take the whole instruction class, all of the heavy functions that we just saw, we'll just lift them out of the CPP file and put them here in the header file and say always inline. And I don't recommend doing this normally, but when it comes to something like an emulator, it's really okay to do this kind of thing, because per instruction overhead adds up so fast in emulation. Oh, that thing. It's probably static in the file. Let's just make it static to the class. Class instruction. Instruction. All right. So oops, sorry about that. Okay, and then we have to fix some stuff here to make it compile in the header. So we need std.io, and then we need to lift some types from instruction CPP. I guess all of these things that are used to create the instruction tables and stuff. We'll just lift those and put them in the header. I have a feeling that this is going to be very, very helpful. But we won't know until we try. Okay, so let's see what's here. Instruction handler. Guess we can just lift that up to the top of the file. And what else is red? Build. Oh, wait, I didn't mean to put these things in the header, did I? Maybe these don't have to go in the header, because they're only used once during startup, so that's not so important. It's just the stuff that we hit over and over and over that needs to go in the header, so that we can inline it into the big emulation loop. And then what else was there? There was like this stuff, like decoding memory or register reference. Decode. Let's just lift that out to the header as well. This is not going to help compilation time, but also like almost nobody uses this, so it's not like a commonly used header. This will make the disassembler and emulator compile a little bit slower, but it really doesn't matter. I wonder how much this buys us, just inlining this stuff. I guess we'll just find out. It's a little bit of a cheesy like optimization, but it tends to work really well. So let's see. X. Ooh, crash. Accessing a null pointer. Wait, how did I manage to do that? Wait, did I put that in the header? That doesn't make any sense. I didn't mean to do it that way. I meant to do it like this. So let's see. And then they should stay here, but they should be extern declared in the header so that we can access them from the outside. Otherwise, we are going to get multiple copies of the instruction tables, because like if you declare something as like static foo in a C++ header file, it's very easy to accidentally have multiple instances of that thing if you include that header in multiple places. And because it's static, the compiler is not going to complain because it thinks like, oh, this is just a file local variable, right? Anyway. Okay, so we're running. See that CPU spiking up here. So the previous one was 27.5 seconds. It's a little bit of a rendering glitch here with the clock sometimes. Oh, it finished. Oh, in 13.8 seconds. Very respectable. Okay. So now we're starting to get pretty serious. So let's run that again, but this time we'll get a profile of it while it's running. Oops. I don't know how I did that. Anyway. Okay, so now we're spending so much time in emulator exec because we've just like inlined the universe into this function, but as we can see, it really pays off, right? And it pays off for many reasons. It pays off because at least I didn't verify this now, but I strongly suspect that the reason it pays off is because it's when everything ends up in one function, then the compiler is able to eliminate a lot of things that are like obviously false every time. Whereas like if everything is in its separate function, then the compiler can't make assumptions about surrounding state. But when you get everything into one function, the compiler can be like, oh, well, this branch will never get taken because like these preconditions here that we know are true because we see the whole code. So anyway, inlining is really nice. So let's see, what do we have? So now, of course, exec, the big chunky instruction decode inlining blob. It's not terribly long, actually. And nothing stands out as super hot here. And the main thing that it calls is read 8, which is the 8-bit instruction fetch. And we've already added the optimization, although there's still like a fair amount of function call overhead here. It would be nice if we could inline it, or at least if we could at least devirtualize the call, because I think it's currently like an indirect call because of the virtual nature of the instruction stream abstraction. So let's see, let's just commit this first. So wait, what was even the speed up? I forgot. It was 15 seconds, is that it? What was that crash? Okay, so say about 15 seconds, that's like, it's essentially like another double speed up, because I saw 13 also. So libx86 apply aggressive inlining to the instruction class, decoding to instruction decoding functions. These functions really benefit from being inlined together instead of being separated. This yields roughly a 2x speed up on there. Okay. So what comes next? Let's try to devirtualize that instruction fetch. So the easiest way to do that, I guess, is to just get them out of the CPP file. So we can just put these in the header, like we already do with other stuff. We just put them down here. Always in line. More of the same. So I hope that it will be able to inline these. I'm not sure if GCC is smart enough to realize that that we're always calling these on a soft CPU pointer from the instruction decode at least. I don't know what's going on here, but we'll get a new one. Okay. 11.8. Okay, so that definitely did something, I think. I wonder if we can like profile the whole thing. Sometimes if you profile for too long, then the profiler falls apart. But maybe we can record a whole profile of this. Let's see. Ooh, we could. Ooh, how cool. All right. So, okay, so it didn't inline it, but at least it made it non-virtual. So that's something. Let's see. That one is definitely unlikely. Let's see. Let's go to instruction. Build opcode tables if needed. There's some attribute for this. It's like cold. Is that it? So like, if you say that a function is cold, then it will just move it away from functions that are hot. And I wonder if we can, I don't know if this will actually do anything, but I want to get it away from the other stuff. But since the other stuff is all aggressively inlined anyway, maybe it doesn't really matter if you make it hot or cold or whatever. That's just me being silly. But what I wanted to do is I wanted to say that it's unlikely that we will do this. So build opcode tables if needed. The fact that we always make a call here, that's unfortunate. Because this is only necessary to do once on startup. And the fact that we're paying for that in every single instruction, that's not cool. We should get rid of that. We could put this in a global constructor thingy instead. So, wait, how's the thing that we do that? We do something like constructor, is that it? I think that's how you do that. I'm not 100% sure. We'll find out very soon. Build opcode tables. So I think if you declare a function with the constructor attribute, then it will run it at startup before main, basically. Is my understanding. Which would be nice, because then we get it out of the emulation loop. Okay. So this works nice and fast. Let's try this. .5 seconds. Okay, so this is not like huge improvement from this or anything. 0.3 seconds. It's probably noise, but it does feel like the right thing to do regardless. So let's make an alias for the profiling. Root home non shellrc. See, can we make a profile? See, like that. Wouldn't that be cool? Oh, so we have two changes here. Right. So first, we're just moving the instruction fetch stuff to the header, always inline, and then this is separate. Move the soft CPU instruction fetch instruction stream to the header. Nah. They don't actually get inlined yet, but at least this devirtualizes them, which is nice. Okay, and then x86. You don't check if we need to rebuild. Don't build opcode table if needed on every instruction. Decode. Instead, just do this at once at startup. Okay. So now we are profiling. Man, these shell aliases are really nice. What's going on up here with the rendering glitch? Weird. Okay. So, so now I see some stuff like this right here could be inline, for example, the implementation of the subtract instruction. And these like generic implementations should also be inlined instead of like pushed to their own thing. So, but like these are not big ticket things. Like the real big ticket is the instruction fetching. So I think that's pretty okay. Maybe I am basically happy with where we got it, although I'm just going to go through the soft CPU, through all of these ops, and just slap always inline on them because there's no sense in these things having their own symbols anyway. Nobody's ever going to call them, and they're not relevant like that. Dum, dum, dum. And it's okay for this stuff to like blow it up and be large code. I don't care about that. Like it's so much more important that it runs fast, because the faster this thing runs, the better tools we can build with it, basically. Like debugging tools are awesome, but if you have to wait like several minutes for something to complete, you're not going to use it, right? So we want this thing to be, you know, reasonably fast enough that you would actually tolerate using it. For like not for like always running programs in this way, but for like running tests. So all these little things help. And obviously this is just like the first pass that we're doing today. This is not like the final optimized program that we're looking at here. This is just me like shaving off a whole bunch of low-hanging fruit. The fact that find region is still almost 10% of samples, that means that we have a lot more work to do on MMU, caching, and optimization and stuff like that. But at least we were able to do a bunch of good stuff here. Taking its sweet time compiling that thing. Okay. Now I'm actually getting a profile. I wanted to just run it normally to see how if it got any faster. But even with profiling enabled, it finishes in 11.4, so that's not bad. So what if we just run it without profiling? Would be cool to break under 10 seconds. I mean, this obviously it's going to be less than 10 seconds if I turn off video recording, but I can't show you that. 11.2, yeah. So we're like slowly inching our way towards the 10-second mark. It would be super nice to inline these fetches. Frickin' instruction fetches. Why can't you inline that? It's so annoying. Let's see. Did I forget anything here? Not really. Okay, so let's just commit these. More always inline on mark some generic instructions with, yeah. Okay, and then how do we get that thing to inline itself? Because the thing is that soft CPU is a final class. And in this context, userspace emulator exec, it knows that it's dealing with a soft CPU here because we have a soft CPU object that we're calling stuff on. So all of this stuff here that we're inlining is using a soft CPU pointer. I guess, but it's probably just getting lost somewhere in GCC, and it forgets that it's a soft CPU, and then it thinks it's just an instruction stream pointer. I feel like they're losing the metadata, but if we templatize this, so instead of having like from stream like this, can we templatize this all the way? I wonder. I mean, since we moved everything to the constructor, maybe we, to the header, maybe we can. So instruction stream type, if we just do like this, will this work? We do the same for the constructor. And then, this is wild, but I think this might work, because then we just forcing the compiler to ignore the fact that we had a base class type before. So removing that information from the compiler, I think it might actually help it. And then from stream, we have to do that here as well. Okay, so if we take away that information from the compiler, oh, now those are private, so that's interesting. So they can't be private anymore since now we're calling them from the template from the instantiated template. We're actually calling them on the final soft CPU type now instead of calling them on the base class type. But that's a good thing. It means that the compiler actually sees the final type. Let's see. Ooh, dude. We made it under the 10-second mark. That's freaking nice. All right, let's just get a profile. I just want to see it. But that counts. We're under. Very, very nice. So we were able to squeeze ourselves under. Oh, look at that, even lower with profiling. So we were able to comfortably squeeze ourselves under the 10-second mark today, which I'm very, very happy with. So now it's gotten completely inlined here. That's awesome. And then we have, oh, this one is not inlined. I don't know why. Well, we can figure that out later. Do we actually instruction stream somewhere? Oh, here. Okay, so we can just templatize these two, since we're already doing this anyway. I just saw some missing missing opportunities here, or missed opportunities. If you're inlining code anyway, it doesn't hurt you to use templates to like improve the compiler's type information for that inline code. I guess this is not really this is like pretty advanced C++ template concepts, but you really want the compiler to have the strongest possible type information about what it's doing when it's inlining something, because that's really when type information can shine, especially when you combine it with things like the final keyword on classes, because the presence of the final keyword here means that if you have a soft CPU pointer or reference, it means that any calls to members of these virtual base classes, like if you call anything on a pointer to this, and since we know it's final, it doesn't actually have to do a virtual dispatch. It can just go directly to the override implementation on soft CPU. So providing that information to the compiler can be really helpful, as we can see here. Since now the compiler knows that we are a soft CPU rather than just treating it as a generic instruction stream. So what was I doing? The decode things, right? So decode, now they take the type like that. Just seeing if we can squeeze a little bit more by fixing these. Because I think that's what this one here is, for example. Non-virtual func to read 32. I bet you that's coming from memory or register reference decode. And maybe, oh wait, do we have read 8? Yeah, it's probably coming from here. So that one is quite high up. So maybe this will actually help more than a little bit. We'll see. This is going better than I was expecting, but that's really good. Okay. Come on now. 8.2 seconds? Holy moly, dude. Okay, now we're getting into some very respectable territory. Down from a minute to 8.2 seconds. That is really fantastic. And oh, we still have that non-virtual thunk. What the hell is that? I don't even know where that's coming from, but still, this is really good regardless. I don't know what these things are. Okay, well, whatever. I'm not gonna figure those out right now, maybe. Although they are bothering me. Who is putting these there? This is another class, okay. Stream, blah, blah, blah. Is it you? You absolute jerk? It might be this one. This is like a generic interface that sits on top of the other ones. So basically, one thing that we're learning here today is that despite aggressive inlining, GCC at some point loses type information, right? Even though everything is right there, for whatever reason. I don't know how their optimization passes are laid out, right? Like you could imagine that they do optimization passes in an order where really useful type information is lost before it can be fully exploited. So I'm not a compiler expert, so I don't know why that happens, but if we force the information on the compiler so that it's available at an earlier stage, then it seems to do better. And here it seems to be like a variant of the same problem, that In this case, we're calling the instruction stream class read, and this, even though everything is inlined, it still is seemingly not aware here that this is a soft CPU object that we're calling it on every time. So these could be devirtualized by the compiler, and actually also inlined. So who calls this? I bet it's these. Okay, so well, if nobody else uses this, I guess we can just hack it here, honestly. So like switch in 2 bytes, case 1, stream read 8. Oh, compiler, why don't you do this for me? But it's okay, I'll do it. It'll be okay. And then M1. Okay. Then we can get rid of this thing. Instruction stream, just get rid of this. Okay. All right. I don't know how much this will do. We'll see, but this should get rid of them at least. And we should be able to inline the last remaining virtual calls. Although they didn't look virtual, they looked non-virtual, just not inlined. But if we can inline them, that's nice. 7.8. Oh, dude. That is so badass. Okay. So, yeah, it's slower with the profiler. The profiler's like, sometimes it slows things down so much, sometimes not so much. I don't know. All right, they're all gone. Amazing. Okay, now this is one big fat function right here. This is the entire instruction fetching, decoding, and dispatch loop. 47% of runtime. That's fair. And then there's going to be stuff we can do in this loop here to make it go better. But I'm going to say we're done here for today. So this is really nice stuff. libx86 plus userspace emulator, devirtualize and inline more instruction code. Use some template hacks to force GCC to inline more of the instruction decoding stuff into the user space emulator main execution loop. Yeah. This is my last optimization for today, and we've gone from 60 seconds when running user space emulator ID to, let's say, 8 seconds. that's pretty respectable. I think that's good. So very awesome, and I think we're gonna be done here for today. So if you made it this far, then I thank you for watching, for hanging out, while we spend some time on optimizing this user space emulator. So I think this is a pretty cool tool. Now it's also a lot faster. 59 milliseconds to execute. It's not bad at all. It's still missing a bunch of syscalls, so we can't run ls. But hello, friends. But it is getting better and better. Oh, we can't do that. It needs some ergonomic fixes as well. How long would it take to run one more instance? Probably a while. But yeah, so I'm really happy with progress on this thing, and it's getting closer to the point where we can start adding some more like Valgrind like capabilities to it. So that's might be what we look into next. So let's see how long that took. 19 seconds to run the emulator inside of itself, running echo. Not bad. All right. And something that I haven't advertised for a while is that if you're interested in supporting my work, then I'm on GitHub sponsors and Patreon, and I have links to those services in the description if you're interested in supporting me. But if you're not, that's fine too. We're all just here to have fun programming. So thank you for checking it out, and I will see you next time.